What's up guys? I'm Engineer Jack. Today, pag-usapan natin ang deflections of beams. So, yung naaral natin sa strand of material, we all know that if our material is subjected to a force, it will deform. For example, meron tayong material na subjected to compressive force, so magkakaroon tayo ng deformation, and this deformation is what we call shortening. But if we apply a tension force for this material, magkakaroon naman tayo ng elongation or yan yung deformation natin. Hahaba yung material. Same case for our material. If we apply shear force, this is the deformed position niya and this is shearing. And also, if we apply rotation in our material, magkakaroon tayo ng angle of twist, and itong topic galing to sa torsion or rotation of our material. So, for our deflections, if we have a beam, simple beam na merong pin support and roller support, if we apply a load, so let's say that these W's in function of X, so magkakaroon tayo ng deflected shape or yan na kulay pula. So, a qualitative deflected shape of a structure is simple a rough sketch of the neutral axis of the structure in the deformed position under the action of a given loading condition. So, this is called an elastic curve. So, ito na kulay pula. So, initially, kung wala tayong load of our beam, itong kulay black na broken lines, that is the initial neutral axis. But if we apply a load for this beam, magkakaroon tayo ng new or final neutral axis na ang tawag natin is the elastic curve of our beam. So, itong kulay pula, exaggerated lang yan. Actually, yung deflections natin for our beam is very small lang. So, syempre, meron tayong origin dapat dito for deflections. So, lagi tayo nag-start ng origin at the left support. Tapos, dito tayo naglalagay ng y-axis. And yung x-axis natin is galing yan sa the initial neutral axis natin. So, for this topic na deflections, gagamit din tayo ng sign convention. So, just like in our shear and moment diagrams, magkakaroon tayo ng external force causing positive axial force if we have a tension force, or just like this figure. But for external force naman, causing positive shear, so if we have a section or a beam, kung kinonsider natin yung shearing force at the left section, that is positive downward. But if we consider the right section, yung shearing force natin is positive upward. So for our moment, this is the external forces causing positive bending moment. So for this section, positive yung bending moment natin. At the left section, pag yung direction niya is clockwise. But for our right section, positive naman yung bending moment natin pag yung direction niya is counterclockwise. So according to this sign convention adopted, a positive bending moment bends a beam concave upward, whereas a negative bending moment bends a beam concave downward. And the sign, so positive or negative of their curvature at any point along the axis of the beam can be obtained from the bending moment diagram. So, para mas maintindihan natin yun yung sinabi, let's say we have a problem here na simply supported beam, na mayroon tayong concentrated load, distributed load, and a moment. If we draw the moment diagram niyan, ito yung drawing niya, so meron tayong positive moment and a negative moment. So, using the signs of curvatures, a qualitative deflected shape of the beam, which is the elastic curve, which is consistent with support conditions, can be easily sketched. So, this is the elastic curve niya. Itong kulay pula. So, as you can see, kung nasaan yung positive bending moment, nandun yung curvature natin na concave upward. But if we have a negative moment, magkakaroon naman tayo ng concave downward na elastic curve. So, itong point, so kung saan tayo nag-zero sa moment, yan yung tinatawag natin na point of contraflexure. O dyan nagbago yung bending natin. So, from positive to negative. And kung papansin din natin yung point niya dito sa elastic curve, dito din nag-start yung change of curvature niya. So, from upward na curvature to downward na curvature. Basta tatanda lang natin itong sign of curvatures natin. If we have positive moment, magkakaroon tayo ng concave upward. But if we have a negative moment for our moment diagram, yung elastic curve niya is concave downward naman. So, we have some methods of determining beam deflections. So, these are some. Number one is double integration method, area moment method, conjugate method, virtual work method, and the three-moment equation. So these are some methods in solving the beam deflections. So for this video presentation, we will focus only for the double integration method. So for example, kuha tayo ng differential element along the length of the beam, and yung length niya is differential x kasi nga yung direction natin horizontal, that is x. So this is differential x. So this is the element of the deformed position. So if we zoom this under the action of load, this is the differential x natin kung nag-zoom in tayo. So meron tayong moment subjected, kaya magkaroon tayo ng deformation or deflection. So this is the deformed position of our differential x. So let's say itong black na broken lines ulit, let's say that is the neutral axis. So yung length niya from this to this point, let's say that is A prime and this is B prime. And for this case upper, let's say this is A and this is B. So gagamitin natin yan to solve our deformation of this differential element. So as you can see, in this curvature, meron tayong tinatawag na R, or yung R natin, this the radius of the curvature, ay nag-start yan from the neutral axis to this point, or yung consider natin na center of this arc. No? So yung arc natin, this the differential S. Gagamitin natin yan to solve the differential equation of the deflection of the beam. So if this differential theta, kalahati niyan syempre is differential theta over 2. So using alternating angles, we can say that this angle din, so from this point na neutral axis natin and this radius na line, so this angle din is also differential theta or over 2 kasi nga that is alternating angles. So ito yung inikli ng A prime, B prime. So meron tayong dalawang differential delta, that's why differential theta over 2. So sum yan is differential theta. So yan yung deformation natin due to bending or due to the load from this differential element or dx. So location natin for this element na itong kulay green na line, that is variable y from the neutral axis. So kailangan natin yan na values in order nga to determine the differential equation of the deflection of the beam. So let's solve this differential delta, that is also equal to A prime B prime minus AB na ginamit natin designation for this, and that is also equal to negative 2y times d theta over 2. So itong formula, nakuha yan sa arc length. So yung arc length natin for our circle, that is S is equal to r theta. So pareho lang in this case. So inassume dito na itong differential element, that is the arc length, and itong length dito na sides, that is the radius. So yung radius, meron tayong dalawang y, and meron tayong angle na differential theta over 2. Simplifying those, that is equivalent to negative y d theta. Now, in our strength of material, yung strain natin or epsilon, that is also equal to the deformation all over the original length. Or yung in this case nga, yung deformation natin na symbol or designation, that is differential delta. And yung original length natin is differential x. That is also equal to differential delta all over differential s. So kasi nga, yung differential x natin is almost or approximately ds na, or differential s. So, halos pareho lang siya kasi nga napakaliit yung value niya. Now, for our differential delta, nakuha natin dito na that is negative y d theta. And for our differential s, that is r d theta. Or yung galing nga yan sa yung arc length natin or r theta. So, this time, yung ginamit natin na angle is differential theta, kaya r d theta. So, magkakancel yung d theta. Ang maiiwan now, for our epsilon or strain, that is negative y all over r, or this r, this is the radius of the curvature. In our Hooke's law ulit, or yung strength of material, we all know that the epsilon or strain, that is also equal to the stress all over the modulus of elasticity E, or equal nga sa derive natin na negative y over r. So simplifying this, we can get the stress is equal to negative E times y, or modulus of elasticity, times y all over the radius of the curvature. Now, in strength of material, yung ginagamit natin na stress or the bending stress, kasi yung stress na magagamit natin dito is bending kasi meron tayong bending moments. So, yung stress natin in bending, that is also equal to negative m times y over I. If we want to compute the maximum bending stress, yung ginagamit natin na variable is variable c, or mc over I. So, syempre, hindi naman tayo naka-max. So, at a certain height lang from a neutral axis yung ginamit natin na y, kaya negative my over I siya. So, equating these equations ulit, magka-cancel yung y, and we can get this equation na 1 over r is equal to m over ei. Ito yung nakakita natin sa libro ng Strength of Materials. But in our calculus, yung radius of curvature natin equation or yung 1 over r natin is also equal to the absolute value of the second derivative of the equation all over, open parenthesis, 1 plus the first derivative squared, closing parenthesis, raised to 3 halves. So itong ginagamit natin equation in calculus. But for our deflection, yung first derivative natin or yung slope of this curvature is approximately 0. Pwede natin itong i-substitute dito sa equation, kaya magka-cancel itong denominator. So, if this is 0, 1 raised to 3 halves, that is 1. Magkakaroon tayo now ng 1 over r is equal to, yung numerator is the second derivative all over 1, or that is also equal to the y double prime, or 1 over r is equal to the second derivative nga. So this is now the differential equation of the deflection of the beam. So we will use this equation of y double prime is equal to m over ei. So for our designations for this deflection or equation, yung ginagamit natin na variable of deflection is variable y. So this is the deflection of the beam at any distance x. E is the modulus of elasticity. I is the moment of inertia about the neutral axis. EI is the flexural rigidity, or ito yung tinatawag ko na strength of the material that will resist bending. And M is the bending moment at distance x. So, if we integrate this equation, integrating both sides, we can get y prime is equal to 1 over EI, the integral of M function of x. So, this is the slope of the elastic curve. So, integrating ulit this equation, magkakaroon tayo now ng y is equal to 1 over ei, the double integration of the moment function of x. And this is down the formula for the deflection at any distance x. So, as you can see, nag-double integrate tayo, kaya itong tinatawag na equation na double integration method. So, para mas maintindihan pa natin guys, yung double integration method, let's solve an example problem. So, for this problem, determine the slope at each end and deflection at the midspan of the beam. Let's say EI is constant. So, yung example problem natin, meron tayong simple beam, pin support and roller support at A and B. And yung load natin is distributed load, yung variable is W. And yung length natin is L. So, first, let's solve the reactions, external reactions. So, obviously, yung AX natin or yung horizontal component reaction about point A or pin A is 0 kasi wala tayong horizontal force. So let's solve the AY or A sub Y and B sub Y. So as you can see, symmetrical yung problem natin. So we can say that A sub Y is equal to B sub Y. So para ma-solve natin yan, we will use summation of force vertical equal to 0. Or pwede naman natin equate lahat ng forces na pataas sa forces na pababa. So yung pataas is meron tayong AY plus BY. And yung pababa natin is just the area of this load that is W times L. So AY equals to BY. So we can say that BY plus BY equals to WL. So 2BY is equal to WL. We can get now the value of BY and AY, that is WL all over 2. So to solve the slope and deflection, we will use this equation. So y double prime is equal to m over ei. So as you can see, yung kailangan natin dito for this equation is yung m function of x. So first, magka-cut tayo for this beam. Magkakaroon tayo ng sections. So pag nag-cut tayo, magkakaroon tayo ng left section and right section. So itong section, let's say, yung length niya from point A is variable x. So, if we get this section, let's say, kukunin natin itong left section, ito yun. So, magkakaroon tayo ng internal forces ulit dyan na meron tayong axial, shear, and bending moment. So, yung kailangan natin is ulit dito is yung moment in function of x. So, to solve this, i-neglect lang natin yung value of B and yung value of A or yung axial and shear. So, magmo-moment lang tayo about this section. So, summation of moment about that section, kung saan tayo nag-cut, is equal to M. or equate lang na natin yung lahat ng clockwise moments to counterclockwise moment. So, yung magkakreate ng clockwise moment about this section is yung reaction lang na AY na WL over 2 times yung moment arm niya is X. And yung magkakreate naman na counterclockwise is yung mismong M, kasi itong positive bending moment natin pag kinonsider natin yung left section. So, sa kabila din yung equation is M, plus yung load natin na W. So, W times X times yung moment arm niya about the section that is X over 2. So, simplifying this equation, we can get the value of M is equal to WXL over 2 minus WX squared over 2. And this is the bending moment equation for this problem. So, substitute this value of M to this equation. So, we can get the Y double prime is equal to, nilabas ko dito yung 1 over EI kasi this is constant. Yung nasa loob lang is yung WXL over 2 minus WX squared over 2. So, integrating both sides, so pwede natin ilabas yung W and 2 kasi that is constant. So, the integral of Y double prime is equal to W over 2EI, the integral of open parenthesis LX minus X squared, closing parenthesis differential X. So, we can get Y prime is equal to W over 2EI times open parenthesis LX squared over 2 minus X cubed over 3, closing parenthesis, plus constant. So, hindi pwede natin kalimutan guys yung plus C pag nag-integrate tayo. So, in this case, C1 yung ginamit ko kasi double integration tayo kaya magkakaroon tayo ng C2. So, this is the equation for our slope. So, integrating ulit this equation, so integrating both sides, the integration of y prime is equal to the integral of this equation, differential x. So, we can get now the value of y is equal to W over 2EI, which is the constant, open parenthesis, LX cubed all over 6 kasi raised to 3 to, 2 times 3, that is 6 na, minus X raised to 4 over 12, closing parenthesis, plus C1X plus C2. So, meron tayong variable X na for our C1. So, this is now the equation for the deflection of the elastic curve. Now, kailangan natin makancel yung C1 and C2. So, to solve the constants, apply the boundary conditions. Ano ba yun ang boundary conditions? At support A, we can say that yung position of our support, that is x is equal to 0, alam natin yung deflection dyan is 0 din. Bakit? Kasi at support, rigid yon, so walang deflection doon. Kaya y equals to 0. So this condition, magagamit natin ito. At syempre, at support B, or at the roller, or yung x naman natin dyan is equal to L. So, yung location niya is equal to L. And yung deflection din doon is equal to 0. So, basta tatandaan natin dito sa deflections to solve the constants or applying the boundary conditions, kung nasan yung support, always yung deflection doon or yung y is equal to 0. So, using this boundary condition, pwede natin yan is substitute to this equation for our deflection. So, let's say, gamitin natin yung y is equal to 0. So, dito sa kabila, syempre, masi 0 na yan. And yung x natin, substitute natin for this equation, 0 din. So, as you can see, magka-cancel ito sa loob. Magka-cancel din ito. So, meron tayong C2 is equal to 0. So, ibig sabihin, walang value yung constant natin or C2. But, if we use another condition na x is equal to L and y equals to 0, substituting y equals to 0 dito sa kabila, and yung L is equal to x. So, simplifying this equation, magka-cancel tayo ng isang L. So, simplifying is y0 is equal to W over 2EI, open parenthesis, L cubed over 6, minus L cubed over 12, closing parenthesis, plus C1. So, we can get the value for C1, that is negative WL cubed over 24EI. So, itong equation, pwede natin ito is substitute for this equation now for our y, but yung C2 natin is 0. So, using that first boundary condition. So, finally, this is down the equation natin for our y or for our equation of the deflection na W over 2EI, open parenthesis, LX cubed over 6 minus X raised to 4 all over 12, closing parenthesis, minus WXL cubed over 24EI. Or we can still simplify this equation. So, simplifying this equation, meron tayo now na value for y that is W over 2EI, open parenthesis, lx cubed over 6 minus x raised to 4 over 12 minus xl cubed over 12, closing parentheses. Or this is our final equation for our deflection. For our slope naman, just substitute the value for C1, which is double L cubed over 24EI, ito yun. And we can also simplify this to this equation. So this is the simplified form, and this is the slope equation of the elastic curve. So para ma-solve natin the problem, kasi ang pinapanap dito is yung slope at each end and the deflection at the midspan. So first, let's solve the slope at each end. So for the slope at each end, yung x natin dyan at the support is x equal to 0 or x equal to L. Yung gagamitin natin, syempre, is itong equation for our slope. So, substituting the value for x, so let's say unahin natin yung 0. So, pag sinubstitute natin yung value of x, yung makukuha natin na equation is w over 2ei times L cubed over 12, or simplifying that is WL cubed over 24ei. And this is radians. So, pag nag-substitute tayo ng values dito, yung makukuha natin, that is in radians. But, kung yung gamitin natin na value for x is equal to L, so same ulit na equation for our slope, yung gamitin natin is L. So, simplifying this equation, yung makukuha pa din natin is WL cubed over 24ei. So, at each end, or the slope at each end, at x equals to 0 or x equals to L, same yung value niya na yung y prime or yung slope is equal to WL cubed over 24ei. After natin ma-solve yung slope at each end, we will now solve the deflection at the midspan. So for the midspan, syempre yung value for x natin, that is L over 2. Kasi yung length natin is L, so kalahati nun syempre at midspan is L over 2. Substitute this value for this equation syempre sa deflection natin na equation. So substitute this value, we can simplify this equation to this, and to this. So meron tayong y is equal to w over 2ei, open parenthesis, negative pi L raised to 4 all over 192. Or we can say that y is equal to negative pi w L raised to 4 all over 384ei. So yung negative, pinapakita niya is yung direction of our deflection. Or ibig sabihin niya, yung deflection natin is downward. So this is now the midspan deflection of our beam or the problem. So finally, these are our equations for our slope na naka-radians yan, and for our deflection na yung direction niya is downward. So para ma-visualize natin yung deflection and yung slope niya, so for our deflection, tatandaan lang natin yung initial neutral axis niya or itong kulay black, and yung deformed neutral axis niya or yung elastic curve. So kung hahanapin natin yung at the midspan, syempre itong value na yon. Itong value na y, that is the deflection at the midspan. But kung gusto naman natin ma-visualize kung nasaan yung slope, ito yung naman yung kailangan natin. So at the support, hanapin lang natin itong point at the support and the neutral axis and the elastic curve. So if we draw a tangent line at the elastic curve, so let's say this itong kulay red na line. So the angle between this tangent line and the neutral axis na initial, ito yung tinatawag natin na slope at the support or at the end support. So ito na makukuha natin na WL cubed over 24ei na dapat syempre yung value niya is in radians. So if you want to compute in degree, just convert. Itong equations, magagamit natin itong formula pag nagkaroon tayo ng problem na yung simply supported lang, kailangan lang natin yung length niya and yung value of weight niya, basta distributed load lang yung load natin of the beam. So, itong formulas, we can use that. And that's it guys. Thank you very much for watching. This is Engineer Jack and have a good day.